In this video, we're going to start to talk about section 5.2.1, the topic of line integrals. All right, so here's going to be at least be our opening motivation. Consider a thin wire that's situated out in the in the plane, kind of like in the picture below. And let's suppose that a function f of x, y measures the linear density at any point, p, on this particular wire. And so maybe what we could say is that, maybe this wire can be modeled by some sort of a smooth curve. The big question that we would have is, could I measure the mass? Could I calculate or determine the mass of this wire? So again, if I have a wire that kind of starts here in the picture at P0 and goes all the way to this like Pn, we'll define what those P's mean in a moment. Well, if I have a wire there and I can model it with a curve, and I have a function f that tells me like the density at any point, then can I determine the mass? Well, in order to do this, we're going to start in the same way that we typically do, which would be we want to try to estimate the mass of the wire. So I'll say, in order to estimate the mass, our strategy is a typical one. Specifically, we will partition the wire into n kind of sub-interval pieces, if you will. And you can kind of see this being done in the picture that I have over on the side, where I kind of have my P0, my P1, my P2, and I kind of have a dot, dot, dot saying I'm going to keep kind of chopping this wire up into small bits of wire. And then I could then say, maybe if I could measure the mass of each of those little bits, I could add them all together, and then I'd have the total. So I'll go ahead and just write that we can use this to partition the curve C, and we plot each point P sub I on C as shown in the picture. So what I would need to figure out is how, once I have this set up, how is it that I could go to maybe say one of these individual pieces here, maybe like P0 to P1, like I just highlighted, and how could I determine or estimate the mass over there? So I'll go ahead and I'll state this. Well, then we could let delta S with a subscript of I, I'm going to have this here stand for the length of a line segment that kind of connects two of these points. That's why it's going to have a subscript of I on it. So if I have my first piece here, this would have a length of like delta S number 1. The next one would have delta S number 2 as its length. And of course, calculating the length of that isn't too hard, because what I can do is I can at least estimate that by saying, why don't I just play connect the dots with those red points? And what you can see that I'm doing here, if I zoom in on the picture, is that I'm imagining playing connect the dots between these two red points. And that's a line I can measure the distance of, because it's just a line, it's not a curve. And so in order to determine that length, that's pretty easy to do. I would just have to say, take the x-coordinate from the bigger point, subtract the x-coordinate from the point before it, add, and do the exact same thing with the y-coordinates. Again, here I'm just using like a little distance formula to make this construction. Ultimately, this is the same thing as arguing that I'm going to be doing the distance in x squared plus the distance in y squared for each one of those segments. And so I'm going to let this here be the length of the line segment from P sub I minus 1 to P sub I. So it's the length of that red line segment. And again, while that's not the length of exactly that green curve, it's pretty darn close. Well, then I could go ahead and do the following. I could say we will select a sample point xi star comma yi star from each piece of the wire, right? So I could kind of go to here and I could select a particular point and I could actually measure what the density is at that particular point. So I'll say I select this sample point and then F of that special point acts as a representative density of the wire on the ith wire segment. So again, I have an approximated length of the wire segment. That's my delta S, I. And this here would represent the length of that, or sorry, the density of the wire at that point. So then I could go ahead and then say, okay, well, if I want to find the mass, I could maybe summarize in the following way. I could say if delta Si is small, like I have a very small piece of the wire that I've selected, I could say the mass of this single section is roughly the same as, here would be my estimated mass. It would be take the density, which is modeled by this f function with my special point plugged in, and multiply that by the associated length. So it's kind of like, how long does this density exist for? So I could then say, therefore, the total mass of the wire can be approximated as, and I could really say that the total mass be, just go through and add up all of these little individual masses as you move down the wire. Start at piece number 1 and go until you hit piece number n. So this is at least kind of the general idea. I break up the wire into small bits, tell me how long the bit is roughly, that's delta S, find me how dense the wire is roughly, that's my F function, and then when I multiply those together, I get a rough mass. I add all the rough masses together to get like a total estimated mass. So the cool thing though is that I can actually see that this could result in ultimately just, well, this looks like an integral from Calc 1. But it's kind of a strange integral. Here's what we could define it as. If f is defined on a smooth curve, so there's a curve that could give me that green wire that we had above, then we will say that the line integral of f along C is given by the following. I would be integrating as I go across the curve. So notice I'm not going to have an upper and a lower bound here because I kind of don't know what those should be. I'm just going to have a little curve here. I'm going to say I'm going to use the wire as kind of what I'm moving along. And then I'm going to be using my f function to measure that like density, if you will. I am going to have a ds to kind of replace this delta s. And again, we can see that that would be equivalent to saying that I'm just going to let the number of pieces of this wire segment approach infinity. And so what we have here is kind of like a classic Calc 1 integral. But the thing that's kind of awkward about it is that it has kind of an unspecified set of bounds, and I have this really awkward differential at the back that's in terms of arc length. Um, Interestingly, as I state down below, you could think of line integrals as being thought of or derived from answering another similar sort of unrelated kind of question. That's what's happening on the next page, and I won't go through that in the next page. If you're interested in taking a look at that other justification or derivation here, you could go ahead and do that, and then of course the notes for that are up online. Our goal, though, in the next video is going to be to say, okay, if this is what a line integral is, I take a function and I kind of integrate as I move along a curve, kind of like what we did up here. I integrate as I go along this curve, and I'm like adding up mass as I go. Then how do you calculate an integral like this? Because this seems really awkward. I don't understand the bounds. This doesn't look like any differential I've seen before. So how would I actually go ahead and evaluate it? We'll take a look at that in the next video.